So, Dana, you ready?
Mm-hmm.
Okay, great. So next up, we have Dana Moshkovitz, who will tell us about reducing non-unique games to Boolean unique games.
Thank you. Okay, so this is joint work with Ronel and Dan from the Weizmann Institute. So let me start by saying that the heart of this work is actually a new testing theorem. And it's a testing theorem for real functions, functions that get real input and have real outputs. And it asks about the degree D part of such a function for D, think of constant D, maybe D equals 1 or 2 or 1,000, but some constant degree. So here is the theorem. So you have a function. So here, for technical reasons, it will be a function on the sphere. I denote the dimension by k, and assume that it has a bounded 2 norm. And now I go and I pick a completely uniform hyperplane. I'm calling it H. Now, what I can do is I can look at this function, the restriction of this function only to the hyperplane, and I can ask, okay, what's the degree D part of this function? Okay, so I should say functions on the sphere with bounded 2 norm have what we would call a Fourier analysis. On the sphere, it's called Gegenbauer analysis. So emission analysis for functions in Rn. But so you can define, so there is a sequence of polynomials and that form a normal basis, and they define kind of the degree 1, 2, 3, and so on part of any function. So this is well defined. You look at the function, you ask what's its part of degree at most D. It's a polynomial of degree at most D. So this is kind of a local view of the function. You only consider what the function is on the restriction to a random hyperplane H. And you can also ask what's the global degree D part of the function. This is what's written here. And then you can restrict that to the hyperplane H. And what our theorem says is that with very high probability over the hyperplane, the local view here is the same as the global view restricted to H, and up to basically 1 over the dimension. And there are some factors that depend on D that we neglect because we think of D as a constant.
Dana, quick question. So the hyperplane means just something with codimension 1, right? It's not a 2-dimensional thing. Okay.
Yes, hyperplane is codimension 1. Okay. Yeah, and whenever anyone has any questions, just ask. Okay, so good. So let's talk about this theorem. The first thing I want you to notice is that we're talking about proximity of functions. Okay, so these are polynomials of degree at most D, right? In k+1 variables, right? So there are many monomials in such a polynomials. In such a polynomial, all those monomials have to be similar, right? It's not just in classical, property testing. There is one property, some Boolean function that you're trying to get right, and here it's actually many functions that you're getting all of them simultaneously close, right? This is what it means that those functions are similar. So this is an extremely strong notion of similarity. So this is the first point. I should say that when we talk about low degree testing for functions over finite fields, we do have a similar notion. The local part, the local low degree polynomial is the same as the globally low degree polynomial restricted. However, over a finite field, low degree functions, low degree polynomials form an error correcting code. So two different polynomials are different almost everywhere, and this is what drives those very strong proximity results. This is not true for real functions. Real functions, low degree real functions are not error-correcting code. So it's quite surprising maybe that you can get such a strong proximity between functions. So that's the first point to make. Second point to make about the quantitative results. This is a tight result, right? You can take a function to be half space and the deviation will really be 1 over the dimension. So you couldn't hope for anything better. I should say, with standard sort of Fourier analysis, right, Gegenbauer or MIT or whatever analysis, you can actually prove such a result. However, you will bound this squared and then get a 1 over k bound, which on the 2 norm, it will give you just a 1 over square root k bound. Okay. So it's, you know, standard to get 1 over square root k. 1 over square root k for our needs would have given absolutely nothing. So the entire question here was how can you get the tight 1 over the dimension instead of what you would naturally get, which is 1 over square root k. Just an intuition for the 1 over square root k, right? We're talking about hyperplanes, right? So we lose one coordinate. One coordinate is like a 1 over square root k weight. Right? If the functions are normalized to have 2 norm 1. Okay. So this is the theorem we prove. We prove it with an interesting technique. So what you can do, you can look at this 2 norm, this difference. You can look at this random variable. You can look at its second moment. And the second moment is a quadratic form that is rotationally invariant. And as such, by Schur's lemma from representation theory, it only depends on the spectrum of the form, right? With respect to some, you know, the sort of Fourier analysis, and not on the function itself. So what we end up doing is consider a function that depends only essentially on one variable. And then what we have is a 2-dimensional problem. We need to look at this vector that defines the hyperplane. We need to look at the direction in which the function actually changes, and it becomes a 2-dimensional problem that, you know, to bound the second moment. Okay. So this is the testing theorem. I'd be very happy to answer any questions about it.
Is something similar true in Gaussian space, or where are you using the spherical harmonics?
So we want to use this Schur's lemma, and as a result, it's convenient to walk over the sphere. Yeah, you can. What we actually need in the paper is a result on you know, RK rather than SK. But we have some extra condition that we can place on the function that makes it look like a spherical function.
Okay.
Okay. Any other questions? Okay. So this is going to be like a Chekhov's gun, right? So this is the gun I'm placing on the table in the first act. And we'll go back to it in the last act. Well, I'll show you kind of analysis, and this will take an important place in it. So right, all you need to remember for later, if you want to know the low degree part of a function, restricted to a hyperplane, it's enough to only look at the function restricted to the hyperplane and compute the low degree part there. Okay, good. So this is the testing, the main testing we'll have in this talk. So this talk is about an attempt to prove the Unigans conjecture. And I should say upfront, we're not trying to prove the full unigames conjecture. We're only trying to prove the unigames conjecture for Boolean alphabets. We'll only fix the alphabet to be Boolean. I'm going to define on the next slide exactly what the problem is. It's a very famous open problem whether hardness of Boolean unigames implies the full unigames conjecture. This is known as the strong pair repetition question. There was a lot of research on it. There is a very famous obstacle, not very, but there is an obstacle, a known obstacle to get this. Recently, there were two works. I was involved with one of them that gave us some reason for optimism. So you can get strong pair repetition in certain settings. There are ways to avoid the known obstacle. But this is all material for different talks. So for this talk, we only care about this Boolean unigames conjecture. Okay, and the starting point for this talk is a paper that Subhash and I wrote up for stock 2016, so 4 years ago, in which we suggested a reduction that would take you all the way from non-NP hardness results to hardness of Boolean unigames. And we suggested a reduction, but we didn't suggest an analysis for the reduction. We didn't know how to prove that reduction was sound. In fact, there was a serious problem with proving that reduction was sound. There was some component that seemed tangential to the main idea, but nevertheless necessary, and it kind of prevented us from proving soundness of that reduction. And I'll point it out as we see the details later. But yeah, so 4 years ago, we did want to to finally get an analysis for such a reduction. After, I think they took 2.5 years of thinking on how to avoid that component that you couldn't live with and you couldn't live without. And what we decided to do was to be less ambitious. So instead of trying to get a reduction all the way from something that is known to be NP hard to Boolean unigames, let's start with something that we only wish to be NP hard. It's very similar in many ways. It has the same spirit, the same feel as problems that are known to be NP hard, but we don't have an NP hardness proof for it. And let's just get a reduction from that to Boolean unigames. And indeed, this is what we achieved in this new work with Ronen. So even after those 2.5 years, it took another 1.5 years to get this testing theorem that I told you about, that allowed us to actually prove that such a reduction works. Okay, so there is this question of, okay, we only showed the kind of a reduction in the air. Really what we want is a reduction all the way from an NP hard problem to Boolean unigames. And the point is, well, if you, right, this is a big gap to bridge to prove hardness of Boolean unigames. And the only way to do it is to do it gradually. And this was our first step, right? 4 years ago, it wasn't even clear that those ideas from the appeal in the paper with Subhash were really the right ones. It wasn't clear that the parameters work out. It wasn't clear how to get rid of this component. And right, doing this reduction kind of made us, prove interesting theorems, and it made us figure out the right way to look at this, to understand how to analyze it, to develop techniques. So this, in my opinion, it was a very useful step. I want to point out that there is a reduction analogous to this reduction that we showed that would go all the way from NP hardness to Boolean unigames. Now, now that we have this proof of concept, we're actually optimistic that we'll eventually be able to analyze that too. Okay, so this is what this talk is about. I'll be happy to answer any general questions now.
Dana, just confirming, you haven't told us about the testing result yet, right? Like the precise testing.
I will not tell you anything else about the testing result.
Okay.
I said the only thing I'll do is I'll use it. Okay, I stated it before. I told you something about how it's proved, and at the end of this talk, I'm actually going to use it to prove hardness of Boolean unigames, assuming this wishful NP-hardness.
Sorry, what was the testing result? Sorry, you must have missed it. What was the testing result?
The testing result was this. It's a low-degree testing theorem for real functions.
So it says that if you have been given a function, then
the low-degree part, you look at the function is defined over many dimensions. You look at the hyperplane, so one less dimension. You look at the low-degree part on the hyperplane versus the low-degree part globally, restricted to the hyperplane. The two are essentially the same. Okay, the local part is the same as the global part restricted back to the hyperplane.
okay,
right, a local theorem. Right, this is a very, very strong. It's not property testing. It's just it's really testing the two functions are similar. Okay, right, but this theorem is going to recur at the end of the talk when I use it. Okay, and for now I want to talk about unigames. Right, this is the subject of this talk, how to prove unigames conjecture. Okay, let me start with explicitly defining Boolean unigames. So this is the kind of an extremely simple extremely simple problem. There are Boolean variables x1 to xn, right? Each one gets a plus or minus 1. And there are order n constraints on them. Each constraint is either the 2 bits are the same or the 2 bits are different. Okay. And right, so why is it called a unique game? So game, maybe we'll talk about games a bit later. But uniqueness, the idea is that if a constraint like xi equals xj holds, and you know the value of xi, then you know the value of xj. And also, if a constraint like xi not equal xj holds, and if you know the value of xi, you know the value of xj, right? Because it's Boolean, right? So this would be the opposite. Okay, so this is the uniqueness. One variable determines the value of another variable, the other variable in every constraint. So here's the problem. I give you this system of local constraints, and this constraint satisfaction problem, and I ask you, can you distinguish whether 1 minus delta fraction of the constraints can be satisfied, or whether only 1 minus, say, 100 delta fraction of the constraint can be satisfied? The 100 is completely arbitrary. It's really any constant that you want. Okay. Another way to kind of the way that algorithms people think about it, which I find a very useful way. Suppose that I give you a system of constraints like that, and I tell you 1 minus delta fraction of the constraints can be satisfied, right? Almost all of the constraints can be satisfied. Can you satisfy for me only 1 minus 100 delta fraction of the constraints, except that you need to be an efficient algorithm? Okay. You don't know what's the good assignment, find for me an assignment that does well. So this is the algorithmic. Let's have like a little ruler here to understand the context. So we know that we have a system where 1 minus delta fraction of the constraints can be satisfied. The best algorithm that manages to satisfy as many constraints as possible is basically this Gomans-Williamson algorithm that satisfies 1 minus square root delta fraction of the constraints with a very specific constant here. Okay, so if you know this, 1 minus delta, the best algorithm would satisfy about 1 minus square root delta. We think that this is tight. We don't know of any other algorithm. Assuming the unique games conjecture, there is no better efficient algorithm, assuming P not equal to NP. And we look at a much harder problem, the problem where we want you to satisfy 1 minus 100 delta, a fraction of the constraints. Right? For small delta, this is much larger than 1 minus square delta. We think that definitely this will not be possible because we think that this is the best possible, not so much. And so can you prove it? Can you prove that you won't be able to satisfy that it's NP hard to satisfy 1 minus 100 delta constraints? This is what I call the Boolean unique games conjecture. For any sufficient delta, it's NP hard to distinguish those two, or given a system, well, this much can be satisfied this much. Okay. And just for reference, the full unique games conjecture is you want a gap between 1 minus delta and epsilon. Right, you're given a system where 1 minus delta fraction of the constraints can be satisfied. You want to satisfy only epsilon fraction. This is only possible if you take a sufficiently large, it's only possible that this is NP hard if you take a sufficiently large alphabet and you take other constraints that are unique. So this is the full unique games conjecture. Okay. Any questions about the unique games conjecture or the Boolean version of the unique games conjecture? Okay. Let's talk about why we care so much about the unique games conjecture. So here is the importance of this conjecture. For decades and decades, algorithms people have been designing approximation algorithms for combinatorial optimization problems by reducing them to geometric problems. Why? Because people have been using linear programming and semi-definite programming. And this is essentially what they do. They take, you start with maybe a graph and you're trying to optimize something, and then you end up embedding everything in like Rn, and you have those linear constraints on them or semi-definite constraints on them. And you solve that, and from that you're able to recover a pretty good approximation. Okay, and this was a very successful paradigm. If you wanted to solve maxcut, it actually led to questions about isoperimetry. If you wanted to approximate sparsest cut, it actually led to questions about embedding. So somehow classical problems in combinatorial optimization led to classical problems in geometry and led to beautiful algorithms. And what the unique games conjecture, well, this comes is actually on the hardness side, and where you ask yourself, those are the best we know, are those really the best possible, assuming P not equal to NP? Is doing better than this NP hard? And the unique games conjecture says yes, at least for very wide families of problems. So for example, doing better than this algorithm for maxcut, assuming the unique games conjecture is actually NP hard, and this follows from geometry. So there is this very tight connection between, very surprising connection between combinatorial optimization and geometry. Basically, the problems, those discrete problems, are essentially equivalent to the geometric problems. And this was extended to any local constraint satisfaction problem. This was also extended by, to covering problems and to many other problems. Right, and you can get like that hardness results that we couldn't get. With the unique games conjecture, we could get hardness results that we couldn't get any other way. Okay, so that's the short pitch for why I care about the unique games conjecture. Again, whenever anyone has any questions, to ask. Okay. So a few years ago, I guess around the time I moved to UT Austin, I realized that the best way to describe what happened with research on unique games is to describe it as a football game. Football game between team algorithms and team hardness. And so let's team algorithms started. They're actually fantastic algorithms for unique games, very strong algorithms. So as I said, when the alphabet Q here is the alphabet, when the alphabet is 2, we can satisfy 1 over square root delta fraction of the constraints. If you want to have large gap, you need the alphabet to be exponentially large in 1 over delta. If delta is too small, so you know that almost all the constraints can be satisfied for very close to almost everything, right? So delta is 1 over log n. They're, again, good approximation algorithms. There are even more surprising approximation algorithms. So it turns out that for random graphs or random constraints, so basically anything random that you inject into the input, the problem becomes easy. And this is in sharp contrast to what we know about other PCPs, about projection games that I'll mention later. The graph can be random, and right, and the constraints can be random, and we still think that all those problems are hard. Team algorithms made more progress with this Aurora-Bragg-Storer algorithm that solved unique games in very large time, 2 to the n, to something that depends on delta, right? So the important thing is that it's not 2 to the n for projection games. We know that the right power here is 1. Under plausible assumptions, the best algorithm we have, we expect to be basically 2 to the n. And no, for unique games, you can do much better. You could do 2 to the n to the maybe 1 over 100. Right? So team algorithms looked like it was winning. It even had a plan of attack. And this is this Lasserre or sum of squares hierarchy of semi-definite programming. It was shown to generalize each and every algorithm that was considered beforehand. And researchers in that area seem to think that maybe it will get you all the way to disproving the unique games conjecture. Okay, how about team hardness? So team hardness didn't do very well. We have various techniques, methodologies on proving hardness of approximation. And what they could give is that it's NP-hard, given a system where 1 minus delta fraction of the constraints can be satisfied, it's NP-hard to do 1 minus something very close to delta, maybe 2 delta. Now is the best, but the constant kind of kept improving, but definitely not better than 2 delta. Was the best hardness that was known. If not much is known, so if you know that your delta is half, right? Your delta is huge. So you only know that half of the constraints can be satisfied, then indeed this is a hard problem, and hardness results were known. Some hardness results. There were also hardness results for basic semi-definite programming, for weak hierarchies of semi-definite programming, but not for Lasserre. A big progress for team hardness was a 2-to-2 theorem from a couple of years ago. So this showed that for this easier case of delta equals half, so you know that only half of the constraints can be satisfied. Now satisfy as much as you can. So this theorem said it's going to be NP-hard to satisfy even epsilon fraction. Now, if you noticed, I erased this plan of attack of team algorithms because this 2-to-2 theorem was a major obstacle for that attack, because if those plans of the algorithms people would have worked out, they should have also been able to prove an algorithm, get an approximation algorithm in the case of delta equals half and small epsilon. And they couldn't do it, right? And they won't be able to do it because this is NP-hard. So at least with the ideas that the algorithms people had, those are ruled out by this 2-to-2 theorem. Okay, and I should say we too have this plan of attack. This is this candidate hard unit game that I mentioned before. Right, basically this idea that we put out for stock 2016. Okay, so this basically on 1 or 2 slides is the entire work that was done on Unigames. I'll be very happy to answer any questions about it. Okay. Good. So hopefully by now we established that the Unigames conjecture is an important problem and that it's not resolved yet. And now I finally want to start talking to you about our reduction. And to do this, I need to tell you what's known in PCP theorems, right? So I told you that we'll prove hardness of Unigames assuming this wishful PCP theorem. So let's talk first about what is actually known PCP, what are known PCP theorems. And this will also give me a chance to explain this connection to games, what's known as two-prover games. Okay, so I want to define for you this object called a projection game. This is the predecessor of Unigames. This is what motivated the definition of Unigames. The current optimal hardness of approximation results we do know how to prove, or proved assuming hardness of projection games. Okay, so what's a projection game? So there are 2 players, 2 provers, player A and player B. There is a verifier between them. Those 2 players, they can agree ahead of time on a strategy, but then they can't, once the game starts, they can't talk anymore. And the verifier goes and it picks some randomness and it uses the randomness to ask questions to player A and player B. And those questions are usually correlated questions, right? Those questions can be something like, here we have some 3-sat instance. Player A, here are these and these and these variables. Can you give me the assignments for them? And player B, here are these and these and these variables. Can you give me the answers for them? Okay. And then player A responds with its answers, or maybe those assignments to those variables, and player B responds with its assignments. And the verifier organizes it so the 2 questions are going to have a large overlap, right? So the question to A will have some subset of variables, and the question to B will have an intersecting subset of variables. So there will be a way, right? So the questions are correlated, and there is a way to test the 2 questions, the 2 answers against each other, because here I denoted the intersection by this light blue. And maybe these are the variables that the two questions had in common, and the verifier is going to check that indeed they give the same assignments to those common variables. Okay, so the verifier usually it checks something on the U question separately, right? Maybe those variables also span various constraints, so it's going to check all the constraints that those variables span. It's also going to check all the constraints that are spanned by those V variables, and it will compare the answers that in the intersection that the 2 questions have in common. Okay, so this is what's known as a projection game. Why is it projection? The projection is like this light blue part, right? In the end, what we do is we check the projection of the 2 answers to the intersection. And then the strongest PCP theorem we have is the following. So we define the value of a game as assuming that the players pick the best strategy for them. What's the probability that the verifier accepts, right? And the verifier accepts if the answers on U separately were fine, the answers on V separately were fine, and they agreed on the intersection. So what's the probability that this happens? And this super strong PCP theorem, what all the known optimal inapproximability results are based off is the following. For any epsilon larger than 0, it's NP hard to distinguish value 1 from value epsilon. So even if there exists a strategy for the players that makes the verifier always accept, so this is value 1, even then, if you are an efficient algorithm, you won't be able to find a strategy that achieves value larger than epsilon. Okay? This is a super, super strong theorem. Okay. As always, if there are questions, do let me know. I should say that various variants on this theorem are known. So for example, you can ask those underlying, suppose that the underlying constraints on U and V would be linear, right? So really, there is some linear subspace, linear constraints on this vector, or linear constraints on this vector. And this is what the verifier checks, in addition to comparing. And even then, it's still known this gap, which is basically gap 1 between completeness and soundness. The completeness now has to be 1 minus delta, because if all the constraints are linear, it's always possible to find an assignment that satisfies everything, right? Because it's just Gaussian elimination. So you have to introduce some completeness error. But it turns out that the completeness error can be arbitrarily small, delta, and you'll still be able to show this big gap is NP hard. Okay, so even though there is a strategy for the players where that they win with probability 1 minus delta, the efficient algorithm won't be able to find a strategy that even satisfies, that even wins epsilon fraction of the time. Okay, let me tell you about another result. So this is a result that Subhash and I proved. So this was talk 2011. This was actually in the when we first started working on this direction to proving the Unigans conjecture, and this we figured out that we need something like that. So standard PCP theorem, everything is usually over, say, the Boolean hypercube. Okay, so everything is usually, say, Boolean or maybe a finite field or something like that. It turns out that you can do everything over the reals, right? So the answer U, this vector is going to be a real vector. The answer V here is going to be a real vector. There are going to be some real linear constraints on U, really linear constraints on V. And the thing about the reals is that then it makes sense when you compare the intersection. It makes sense not only to accept when the intersection is exactly the same, but to accept also when the intersection is quite similar. And what we showed is that even if you count similar intersection, like L2 norm, as this is fine for the algorithm, even this is going to be hard for the algorithm. Okay, so even if you allow on those common indices to have well, this is just UI minus VI, to have a distance square root delta, even then it's going to be NP hard to achieve value, a large constant value. Okay, so this is what we call a robust, call it robust linear equations over the reals. In other words, right? So if you're trying to solve the real linear equations, it makes sense to do something like how is it called? Mean squares, right? Which would give you wouldn't have exact satisfaction. The linear constraints would not be exactly satisfied. You will be close to being satisfied. And we show that this is best possible. Okay, even if you allow this approximate agreement on the intersection, even then the algorithm cannot do much very well. Okay. Questions about this? This is the version that is most relevant to what I'll talk about next.
So I have a question. Is there a qualitative sense in which this result over reals is like better than what is known over finite fields? Like, I mean, I can still see the same root.
You say qualitative or quantitative?
Well, either sense actually.
No,
I didn't
think
exactly understand the
both
importance.
senses. Yeah. Okay, so let me emphasize it. When you talk about discrete linear equations, the only measure of how successful an assignment is to ask whether the equation is satisfied, whether those two things are supposed to be equal. Are they equal or not equal? There is no sense in which you can be a little equal, right? Either it's equal or not equal. I guess you can ask on how many indices are equal, but I mean, it's either you have equality or you don't have equality. When you talk about real assignments, you can ask how close they are to being the same, right? Right. You can ask ui minus vi, right? Which is right, and then to say that you can't even that they can't even be close, right? It's a much stronger qualitatively sense than it is to just say that it's not satisfied exactly. So it's a much harder theorem qualitatively. Right, we use all the standard things that are used all the time, but we also need to prove robustness, which was quite difficult. Now, you asked about the quantitative aspect, the square root delta. I should have said that the square root delta is exactly the right thing you would hope here, right? Assuming that there is a strategy where there is 1 minus delta. With probability 1 minus delta, they agree exactly. Kind of this mean squares algorithm, which is basically a semi-definite programming algorithm, would get you a deviation of square root delta. Why? Because what it would do is it will minimize the squares. It will minimize the L2 square, and the L2 square in the completeness case would be delta, and so in the soundness case, all you can hope for is also delta, but this is L2 squared. So if you go and look at L2, it's square root delta. Okay, so this is the square root delta is exactly tight. It shows that semi-definite programming is tight for this problem. Okay, and it's exactly the square root delta here is the same square root delta that you'll see throughout this talk. It's always the same issue, that what efficient algorithms can do is optimize in L2 squared. And if they optimize in L2 squared, then what you can say about the L2 difference is, you have this square root. And this is the entire question of Boolean, hardness of Boolean unit games, whether you can do better or you can't do better. Okay? I hope that this answered the question.
Yeah, got it. Thanks. Yeah, got it. Thanks.
Happy to answer other questions. So here's the shortcut that we allow ourselves in this work. So in this projection game setup, the situation. Oh, and I should say also we can make sure that the intersection can be very, very large. I mean, maybe you'll pay here in the gap for this large intersection, but the intersection will be very large, and we'll still have an NP hardness result. Okay. Now in all those discrete, all those PCP theorems that we're able to prove, what happens that the player knows that the projection, the intersection where it's going to be asked, is in a subspace that is parallel to the axis, right? It's on coordinates. So this player A has all those coordinates it needs to give. It has all this vector that it needs to give, and it knows that it's going to be compared on some of those coordinates. Okay, but it's definitely going to be compared on coordinates. And the shortcut that we give ourselves, the reason it's only a wishful PCP theorem rather than a PCP theorem we can give, is that we're going to define this variant of projection games where the intersections between those two vectors are not on coordinates, but on general hyperplanes. Okay, so let me define it exactly. So this is what we call the subspaces near intersection game. So again, there are two players, player A and player B. each one gets a linear subspace in Rk, R to the k. Linear subspace. This is what represents the constraints that we have on the vector, the linear constraints. And then there is some hyperplane that the verifier has in mind. It's a specific hyperplane, and it's not telling anyone the hyperplane, right? And this is what corresponds to the intersection in coordinates that we had before. And now each player is supposed to answer with a unit vector in its subspace, as in a unit vector that satisfies the linear constraints it knows about. And what the verifier is going to do is it's going to check the projection on the hyperplane of each vector, and it's going to check whether the projections are the same. Okay, so this is subspaces near intersection. Right, so subspaces because we have linear subspaces, near intersection because we don't check that the two vectors are the same. They have to agree on a hyperplane. Okay, so this is the game. This is the projection game we want to work with. Okay. Oh, I should say another comment. I'm talking here about objects that live in real space. So what do I mean? Obviously, how do we represent real numbers? So what I mean is that we choose some precision. Precision is much, much higher than any other quantity we care about, all those deltas and whatever. And we represent numbers, real numbers, only up to that precision. Okay, and then of course there are going to be precision errors everywhere, but they're not really, they're inconsequential, so I'm going to ignore them. Okay, but this is what I mean, right? Real numbers are represented up to some very, very, very large precision. Okay, and this is the game. So here is what one can do with semi-definite programming. Suppose that there exists a strategy for the players that is accepted with probability 1 minus delta. As in, the projections are exactly the same with probability 1 minus delta. What can you guarantee efficiently? If you write the semi-definite program, what you can guarantee is that the projections, the L2 squared distance between them is at most delta, which corresponds to the L2 difference is square root of delta. Okay, so why is this? Because the fact that there exists a strategy that is accepted with probability 1 minus delta means that with probability 1 minus delta, the two things are going to be 0. So this would be 0. And then with probability delta, those two things can be maybe 1, right? Because it's unit vectors. So I get this bound of delta on the L2 squared from the completeness case. And so we expect the same in the soundness case. And this would guarantee L2 difference, which is square root delta. And I can guarantee it with high probability and with some constant here. Okay, so this is what SDP can do for this game. And this wishful PCP theorem, our conjecture is that this is going to be the best possible for this game. And if you believe that this is best possible for the game, then we can prove Boolean hardness of Boolean unique games. Are there any questions about subspaces near intersection and hardness assumption? Okay, so this is the main result. Hardness of subspaces near intersection implies the Boolean unique games conjecture. Okay, so let me tell you about the methodology. How do you prove hardness of approximation results in general, right? Ever since the 90s. So we have this projection game where there are questions to the players and there are answers, and there is this verification. And the methodology says what we're going to do is consider an encoding of those answers. And usually, right, it's a Boolean encoding, usually via a code that is called the long code. And you should think of our new variables as those bits in the encoding. So you have those variables and those variables for all possible questions to the players. These are going to be your variables in the unique game or in whatever you're trying to prove hardness of approximation for. And what you'll do is try to simulate the test that the verifier wants to do, which is maybe the test here or test here. And you will simulate it by maybe unique tests on those Boolean variables here. Okay, so this is the general methodology for proving optimal hardness of approximation. It's a very successful methodology in general, right, to prove various hardness of approximation results. Right, you just encode and you try to simulate the verifier using those bit constraints on the bits. And this is what we'll try to do here too, except, right, so first of all, we'll start with the subspaces near intersection game, right, well, we have these. And except that we'll use a very untraditional encoding scheme, which is encoding by a half space. And what do I mean by that? This player is supposed to answer some vector, right? And this player is supposed to answer some vector. The encoding of the vector, we're thinking of this vector as defining a normal or defining a half space. And here we write the truth table of this half space. I see a question. Okay. So yeah, it was a reminder that I should finish in 10 minutes, which I will sort of do. The idea of encoding answers with half spaces was the major idea in the paper with Subhash on how to prove hardness of unique games, right? Instead of using the long code or other codes that are used here, just encode a vector with the half space that the vector defines. Again, right, this is over Rn, we do everything up to precision. Okay. Why is this good? Because we can do various tests. Maybe let me not. The main tests that we're going to do are two. We're going to check. We're going to do a noise test. What's a noise test? So what's special about half spaces? Why do we want to encode as half spaces? Half spaces are known to be the solution to the isoperimetric problem in Gaussian space. If you do this noise test where you take a random, say, Gaussian point in Rn, and then you perturb the point a little, you shift it along a random direction give it a small weight, and you ask whether it changed the function or it didn't change the function. So this is the noise test. Its importance is that it's one of the only tests that we can do if we have Boolean unique games, right? Because it checks equality between bits. Okay, there are very few things you can do with equality between two bits, but the noise test is one of them. And half spaces are the functions that maximize the acceptance probability of the noise test. Okay, this is why we picked this half space encoding. The other thing you can do is you can check that those two functions actually agree on the hyperplane. Right? That if they're supposed to be the same on the hyperplane, then you can test it. This is again something that you can do with a unique test. The other thing you can do is do various linearity tests on this function. But this is it. This is the entire hard Boolean unique game. Okay. Questions? So this is my last slide. I'm going to outline the entire analysis of this Boolean unique game. Right on one slide, I'm going to use the testing theorem that I mentioned in the very beginning. Okay, and there are going to be 4 steps to the analysis, and all of them are quite natural. So here's what we do. Okay, so first of all, we have this consistency test where we check the 2 functions on the hyperplane, and those are 2 right. Those functions that we talk about are Boolean functions, right? They're supposed to be subspaces, right? These are Boolean functions, and we know that our right typical answers are the same. Using hypercontractivity, we can show that the low degree parts, right? We pick some degree which is a sufficiently large constant. The low degree parts are going to be close in L2 difference up to delta. So this is the first step. This is where we use the consistency on hyperplanes. Now we finally use the testing theorem. As I told you, the testing theorem is basically works smoothly on the sphere, and we want to work in Gaussian space, and we have this trick to basically move to the sphere, right? Forget that. The main issue is that the degree D part of the function is the same, right? We can put the degree D inside. Right, so it doesn't matter whether what you do is you take the actual degree D and then you restrict it to the hyperplane, or whether you take the function restricted to the hyperplane and then consider the degree D. This is the same, essentially the same. Now we need to use the noise test. Right, notice that the entire a Boolean hard unique game, it has basically 2 or 3 tests that you do. Right, it's basically consistency and noise, and maybe some testing linear constraints. So here we use the noise test because the function is noise stable. We know that it has a substantial low degree part, right? For say 0.9 for some large constant. So here is what happens. So per question to the prover, what we have is the degree D part of this function. And we know that those degree D parts of the function are consistent because of what we just proved. So they're consistent on the hyperplane, right? Which is almost what we wanted, except that what we really wanted is a unit vector per question rather than a degree D part. So kind of the majority of the analysis now is just to show that from degree D parts, you can actually get unit vectors that are similar. And we do that just by differentiating the degree D part, something like D times, until we get unit vectors. But this is it, right? This is the entire outline of the analysis. I think that I even have 2 minutes to spare if anyone has questions.
Thank you, Dana. Are there any questions? Actually, okay. I have a question. Is there like a succinct way to say why 1/k was critical, or why something greater than 1/√k was necessary for your analysis? Is there a simple is it possible to see at this level of discussion, or is it much more intricate?
Yeah. The issue is that you need to look at parameters of subspaces near subsection.
Sorry, there seems to be a lot of feedback. I don't know why. There seems to be a lot of feedback.
So this should be better.
Yes.
Right? Yeah, so this problem makes sense, right? You don't want, right, if you picked K to be very large, right, what happens is that this problem becomes very similar to, it basically becomes unique games, right? Because you expect a 1 over square root K difference between the projections. Okay, just the provers cannot do anything, can do almost nothing and still get a 1 over square root K. Getting 1 over square root K difference is not interesting, right? This is only interesting when K is about something like 1 over delta or something like that. Well, 1 over square root K is large, whereas to get a delta difference is small. So we don't want to lose 1 over square root K. This would give you, will kind of not make it an interesting problem.
Are there other questions? Well, there doesn't seem to be any other questions. Well, in that case, thank you, Rana, and we will resume in a little less than 15 minutes at 3:45 Eastern time with next Epis Costas. So we'll resume in 3:45 in 10 minutes and 10 to 15 minutes. Yeah.